So, okay, when I say that L models ZF, what I'm saying is that we assume that ZF holds in the big universe, so that it's a model of it, and then we look at our formulas and say, oh wait, they also hold when relativized to L. Because L is transitive, we get extensionality for free. If X is equal to Y, then X and Y are both subsets of L, so L already knows that they're the same. Pairing, we just saw that finite subsets of L alpha are members of L alpha plus 1. There we go. So if X is a member of L alpha, then the union of X is a subset of L alpha. Because all the members of X are members of L alpha, and they are subset of L alpha, so their union is a subset of L alpha. And whether we write and whether we hang an L alpha on this or not, as long as we're talking about a member of L alpha, nothing changes. Yeah, it almost looked like L was equal to that, and that is not quite what I wanted to say. Infinity omega is a member of L omega plus 1. Done. And the fact that it does what it does is a simple enough formula that if you check what omega does, what should it do? Well, it should this is what omega should satisfy. And it's the smallest one, so this defines omega, and that tells you that it's a member of L omega plus 1. You could also identify and maybe that is easier. Omega is just the members of L omega that are ordinals, so omega is a member of L omega plus 1. We checked that already. 1, 2, 3, 4, 5, foundation. We're in a universe where we assume foundation, so okay, these two I do simultaneously. You may remember way back in the beginning that I said something about the formulation of these two axioms. The formulation was For every x, there is a set that contains all the subsets of x. At that point, I didn't say which consists exactly of the subsets of x. The same with replacement. If we had a thing that looked like a function and we had a set in its domain, then there was another set that would contain the range of that thing. And this is the place where that's going to make life easy. For example, oh, almost forgot. It was at the top of a page somewhere. We have a rank function for the members of L. Just like in the case of V, we look when it appears for the first time, that has to be a successor one. So we take the first ordinal where it is a subset, but then subset alpha plus 1 is where it's a member. And that's a well-defined function. So, pardon?
What letter is it?
It's supposed to be a row. Greek. What can we do? Well, we can look at the power set of x, but we're only interested in the ones that are constructible. That's a set. Look at the ranks. That's a set of ordinals. Okay, the ranks plus 1, just to be sure. The supremum of that is still an ordinal. And so what do we know now? We know that for every L that happens to be a subset of X, every member of L that happens to be a subset of X, we know that it's a member of L alpha. And so we have a member of L that contains the power set of X as far as L is concerned. Because power set is definitely something that's relative. It depends on the model where you are. And likewise, you can do the same trick for the replacement scheme. You take the situation and then we know that there is a set of ranges in V. We intersect it with L and we take the supremum of the ranks, and that's where we are. I wrote it down in my notes so you can have a look at it, or you can cook up your own proof for that. That's why I took these two together. So what's lacking? Separation. Okay, well, and so the free variables are shown here. And Notice the L, because we're talking about L itself, and so we relativize everything that we have to L. This has to work inside the model L, so we only can use quantifiers restricted by L. Well, we know this. So now the big question is this.
This is by transitivity, right? You know, Z is in L alpha, so every element of Z is also in L alpha.
Mm-hmm.
So this just
I would say the only difference from left to right is where can my zeta and w be, right? If they're parameters taken from which set.
They're all in...
I know that they're in L alpha, so the formula is the same.
No.
But the quantifier can be...
The quantifier. Right.
There could be a quantifier for every P. That would become for every P in L here, and for every P in L alpha here, and there is a subtle difference there. No, not quite subtle, a really big difference. Here you would have a set of P's, and here you would have a proper class of P's. The same with an existential quantifier. I mean, here something has to hold for all P's in the whole universe L, and here only for the P's in L alpha. But likewise, if there is an existential quantifier, and there happens to be one in L, you're screwed if there is no one in L alpha that does the trick. Because then suddenly the two formulas don't say the same thing.
if it's true for all the existential quantifier, you can probably sort of fix by saying if it's true for all in L, then it's also true for all in L alpha. And for existential quantifiers, there's only going to be countably many of them. So you can take the supremum of their ranks, and then...
Yeah, well, then we're not talking about alpha anymore.
No, then you're not talking about alpha. But that's fine, because we're talking about the entirety of L. So we just need to show there's some beta then, which can be God only knows how much higher.
Well, it's not God. It's Leeuwenheim and Skolem.
I'm liking that now.
The proof breaks down here because there is something that we have to show that we cannot yet. What we shall see is that actually the class of betas with this particular property is proper. It's cofinal in the ordinals. Because that's going to be the net result of our of the things that we're going to be doing the coming weeks. We'll be able to find a beta most likely way bigger than alpha. You could be lucky, it could be alpha itself, but so let's be generous and leave open the possibility that alpha is already doing it. And then the set that we are worried about is not necessarily in L alpha plus 1, but it's at least in L beta plus 1. Which is good enough because we want it to be in L. So that, and this is the point where I was going to talk about all the formulas not being a set and everything, but Mr. Wise Guy here had to ask.
Next time I'll not ask a question if I don't understand something.
Please do, because I want to make jokes like this. So this is one, and why did I say Leuvenheim-Skolem? Because this is the Leuvenheim-Skolem theorem. It guarantees that this kind of thing happens lots of times. Actually, it's more Skolem than Leuvenheim, because Leuvenheim did it only for one thing, and Skolem did it for all theories and everything. But that's beside the point. So we were almost, well, almost. We were almost there having our model of set theory. We were still quite far away from having the axiom of choice and the generalized continuum hypothesis in it. But we were this close to having a model. So what do we have to do? We have to understand the relationship between this and this better. Because we want as many instances as possible where these two things are basically the same. I mean, the more it's the same, the better, because then we don't have to worry about what's hanging on our formula. And so we need theorems that will tell us, yes, that's going to be the same thing. And then, preferably, we would like to then define the definable subsets in terms of those simple formulas. But then we cannot use the formulas themselves. We have to find yet another trick to sort of encode those formulas in some type of other operation that's purely set theoretical. So there is still some work to be done. We're not going to finish today. Because the remark that our friend made at the beginning is that what we have done actually is nothing, because the definition of def M is not formalizable in ZF. It is formalizable for us outside the theory, But that's not good enough. We need something that can be described completely in terms of sets. Okay, so what is that going to? What's that going to be? Plus, we need to get a handle on this difference. Where do we get those betas from that suddenly get this magical property that you can jump back and forth between the whole universe and just a sub-universe and without losing truth? Well, and there's going to be a very, I think, a brilliant trick. This is mostly this is coming from Jech's book. Koonin has a completely different approach. I'll mention that later. Well, completely different is maybe not the word. He does the same thing, but he formulates it differently. We're going to be looking at simple formulas. And it turns out that to define def, those are the only formulas we need, if we do it cleverly enough. Okay, a delta zero formula, there is delta, there is pi, and there is sigma, and I'll talk about pi and sigma later. Those letters were introduced by Levy somewhere in the 60s to classify formulas according to complexity, and the complexity was the number of quantifiers that were in there. Delta zero formula, essentially it's all the quantifiers are bounded, if any, but let me any formula without quantifiers is a delta zero formula. And as you know from any logic course that you have taken, we don't need to look at those other three. As long as we know that these two work, we can make all the formulas anyway. But just to be sure, I'll stick them all in. If I have delta zero formulas phi and psi, then all these are deemed to be delta zero as well. And if phi is delta zero, then so are these. Okay, purely formally, the official formal definition of this is this. But I'm not going to write this all the time. I'm going to stick with this abbreviation. Okay, lovely. What good are these formulas? Well, suppose you have a transitive set, and you only need a transitive set. No, it doesn't have to be a model of anything. Although after a while, we're going to put more and more demands on the M that we're talking about.
in that definition, does y occur in phi, or is it a free variable?
Could be.
Could be a free.
It just doesn't matter. Basically, the point is we put a quantifier in front, and we have this x element y and phi after that. So, and this is that abbreviation. But yeah, conceivably, y could be in phi, could be bound, could be free. We don't care. Well, you know, phi could be x element y, and then it says there is an x in y such that x is in y. And okay, that's a true formula, but not very informative. I mean, they don't necessarily have to make sense as long as they're well formed. All right, this. If you want to check, and I mean, this is one of the things we're looking for, we just can drop the whole m. So in that, if that formula that we had over there was a delta zero formula, then we had an L here, which we could drop. We had an L alpha here that we could also drop because L alpha was transitive. Oh, and in that particular case, we did have the separation thing. Except that was only a delta zero formula and not one of the more complicated ones. But you can see where this is going. We're going to be looking at, can we get as complicated as possible while keeping this idea? And so this is the first step. Delta zero, yes. If we have something that can be expressed in a delta zero fashion, then we don't have to worry about its truth or falsity depending on the transitive set that we're working in. As if we check it inside a transitive set, check it in the real world, in the big world, will be the same answer. And of course, then we have to prove this. Formulas without quantifiers, these are two formulas without quantifiers. They're definitely delta zero, and nothing is happening here. And of course, if this is a negation of something, the negation is equivalent to the negation. So, yay! If this is a conjunction, then the first conjunct is equivalent to the first conjunct, the second is equivalent to the second, or something like that, and there you have it. So, if we take two formulas for which it works, it still works. So that this takes care of all the quantifier-free formulas. And we only do the existential quantifier. The universal quantifier is not existential not, so easy enough. Okay. Okay, now in this particular case, I take the bigger version of it. So I assume there is an x in y such that phi holds, and I put an m over it, but I put an m over this. So putting an m over it means there is an x in m. Putting an m over this has no effect, so I'll drop it, and I only have to stick the m on the phi. So this is what I get. But it means that I can take there is an x in y, I can take it out of the m, because these two together still mean there is an x in y because of transitivity of m. By assumption, these two were equivalent, and then simple logical syntax rules and then formal proofs will tell you that these two are the same. So if we start with this, we can drop the m, and you can almost go backwards. Say, well, if there is an x in y such that phi, then there is an x in y such that phi m, because these two are the same anyway. Oh, but because we're transitive, we can make this of it, and we're there. So those delta zero formulas, like I said, are, and here is the important word for the day, absolute for m. If it's true in m, it is simply true. And that is what absoluteness means. I mean, I'm just saying the word, that is what this, we phrase this as phi is absolute for m. Later we will have two models, and then we'll have an absolute for m and n, or whatever they are called. We could say that they're absolute for m and the universe, or something like that. And by the way, absoluteness is one of the things that people stumble on in the beginning, because it can get tricky every now and then. We'll see how tricky it will get. Do we know any delta zero formulas? Well, we had two x equal x element y and x equal y. But you can, many things are simply delta zero by their definition, and other things are delta zero by theorem. In Jech's book, there is a long list in lemma 1210. I'm not going to copy this on the board, because that would only be boring. In Kuhnen's book, it's a little bit spread out over the chapters, but most of it happens in chapter 4. Both introduce the concept of delta zero formula. In that case, they're the same, but the way they handle the delta zero formulas and work with them is quite different. Jech is a little bit more loose. You just say, okay, that's all delta zero. Here are the formulas. Kuhnen is a little bit more careful, or some might say a lot more careful. Okay, Okay, Yes says all the things are delta zero for transitive models, and he doesn't really say what of. Kunin says things are delta zero, period, because you can write them down in delta zero formulas. Others are delta zero for models of. Now, why is that? That's because sometimes you need a bit of ZF to actually prove that your notion has an equivalent delta zero formulation. I'm not going to go into all the details, but let's being a subset is delta zero because you quantify over the elements of X. And that's a bounded quantification. These things are delta zero because it says, well, X is a member of Z, and for every U in Z, U is equal to X. X and Y are members of Z, and for every U in Z, U is equal to X or U is equal to Y. That kind of thing. This is a little bit more tricky, but not overly more tricky. You need first to take elements of Z and then elements of those elements, and then you can write down only using equality and element of to express that Z is the ordered pair with those second things that you took out of the members of the members. Well, the empty set, the union, intersection, difference, the successor function, union and intersection of families. Kunin explicitly says the intersection of the empty family is by definition empty. Although strictly formally it would be the whole universe, but that is not a set. So, and that's not quite delta zero. X is a transitive set. The very definition is delta zero. For every Y in X, for every Z in Y, Z is a member of X. And so now, being an ordinal is delta zero. Because now we can use, through foundation, we can say it means transitive and linearly ordered by the element of relation. And when you write that out, you get a simple delta zero formulation.
Would it not be delta zero if you didn't have foundation, if you had to write down by order?
Well, then you would have to say that for every subset, there is a minimum.
But isn't that bounded quantification for every bounded subset of?
No, because who says you have the power set in your transitive set? And when you say, wait, for every subset of X, here it will be for every subset of X that is in M, there is a minimum. And here it says, for every subset of X in the whole universe, there is a minimum. That may not be the same thing. That's the trap I fell into in the beginning too when I was thinking about this absoluteness. Yeah. Wait a minute, every subset has a minimum. Yes, but this suddenly makes your family of subsets way smaller, and you have a very small demand rather than a really big one. Limit ordinals and successor ordinals are also delta zero. For every X in Y, there is a Z in Y such that X is a member of Z. if you know that y is a limit ordinal, if y is an ordinal and you have this extra thingy, then delta zero formulation that it's a limit. And the other one, there is a member of x or y or whatever that acts like the maximum. And then it's a successor ordinal. So that is what delta zero formulas do for you. If you have a transitive set, it could be very weird, but still transitive, then you can recognize the members that are ordinals simply by looking at them and checking whether they're ordinals in the real world. You can check whether something is an ordered pair of other members of the set just by looking at it and say, yep, that's fine. Because in transitive sets that doesn't matter because of the formulation. Now there are things that are also absolute, and I want to write down what absoluteness means, and then we'll talk a little bit more about it. Especially what the difference is. And maybe I'll talk about this next week. We can cater to classes too in this particular case. We'll do it in the informal way, but you can do that in the formal way through formulas as well. But that makes life a little bit more difficult. And neither Jech nor Koenen does it in that formal way anyway. Okay, I'm not going to write everything down. You can fill in the letters yourself, or you just read them from my notes. There are two kinds of absoluteness, up and down. If you after some checking have found that for all members of X, for all members of M, whenever this is true, that is also true, then you call this upward absolute, because as soon as you have checked this in M, you know that you're not going to get any new information when you move to N. The new members of N will not help you in deciding this for the points in points X. And vice versa. This says that if you have checked it up there, then you have used too much information because you could have checked it already here. Or too much information. Anyway, you can check it with less information as well. And of course, absolute is both ways. Now, there are some things that are not absolute. Any idea?
The number of elements.
Cardinality is not absolute. Because the cardinality for N is probably smaller than the cardinality of M, because there are more bijections here, so it's easier to get a smaller ordinal. So you can have a set in here that thinks it's uncountable, and out there it's just countable. We talked about this in the beginning when we talked about Zermelo being angry at Skolem for showing that there are countable models of set theory, simply because it was a first-order theory with a countable language. That's not possible. What? That's not real set theory. Yes, but nevertheless, you can assuming that ZF or ZFC is consistent, you can build a countable transitive set that acts like it's all of V, and it has a thing in it that is the real line, and that it thinks is uncountable, just because none of the bijections that we obviously see from the outside is in that particular structure. They are not members of that structure, and therefore they don't count. Power set is not absolute, because what is the power set usually in a transitive subset? It's the intersection of the real power set with that transitive universe. And again, in that countable model, the natural numbers have only countably many subsets. So that's not going to be the full power set in there. That kind of thing is, of course, not absolute. What is absolute between what and what? Well, if we follow Koenen's book, then if you read Koenen's book, you'll see that very often he assumes that the model satisfies ZF minus the power set axiom. Why? Well, there is a bunch of models or structures that satisfy ZF, but not the power set axiom, and they're still quite useful. So anything you can prove about them is useful. So for those, with those models in mind, he explicitly uses this. Let's say M in the universe. So M, and it's transitive, by the way. That's almost a standing assumption now. If M is transitive and it satisfies ZF minus P, then being finite is absolute between it. Oh, wait a minute, it's already. Okay, I'll leave you to think about this, how you would do this, and then we'll do that after the break. And I can replenish my teacup.